In this video, we're going to talk about intermolecular forces. So intermolecular forces are between different molecules, whereas intramolecular forces exist within a molecule. Basically, the bonds that exist between like a carbon and hydrogen and methane, or hydrogen and oxygen and water. And there's four main types of intermolecular forces we're going to learn about. The first one is ion-dipole. Then we have dipole-dipole forces, hydrogen bonding, and London dispersion forces. So essentially, the strength of the intermolecular forces that you observe has impacts on things such as boiling point, vapor pressure. It has effects on viscosity, surface tension, among other things. So that's why we learn about it. It has large impacts with how matter organizes itself in the world. So which ones of these are observed depend on the polarity of the molecule. So if you have polar molecules, you have dipole-dipole forces. And if that polar molecule is interacting with an ion, you're going to have ion-dipole. Now, if you have a super-duper polar molecule that has something called hydrogen bonding, well, that is then more powerful than dipole-dipole. We'll get into these all individually. And then London dispersion forces are the weakest of the intermolecular forces, but when you have larger molecules, they can add up collectively to be very powerful and impactful. So to determine whether or not a molecule is polar, you have to look at two things: the type of bonds that exist and the molecular shape. So if we're looking at these three up here, this is a linear molecule. We have two different elements. You got hydrogen and fluorine. Fluorine having a substantially higher electronegativity than hydrogen. The bigger the difference in electronegativity, the more polar that bond is. But you can't just look at the difference in electronegativities and say that's polar, because sometimes you have molecules like this CO2 over here, where oxygen has an electronegativity of 3.5 and carbon 2.5. That's a large difference in strength between the atoms. However, because it's a linear shape, so it has no unshared pairs of electrons on the central atom, and it doesn't have different elements bonded to it, so you essentially get symmetrical pulls or forces pulling the electrons away from the central atom, thus canceling each other out, like a game of tug-of-war where you have two people evenly matched on opposite sides. However, if you look at a polar molecule like water, you have a bent shape. You have two, they're not shown here, but you have two unshared pairs of electrons here, thus promoting some asymmetry within the molecule. So, molecule is polar if it either has unshared pairs in the central atom, because that's going to lead to it being asymmetrical, or you have different elements bonded to the central atom, and that's going to result in different strengths in pulling electrons from the central atom. So first I want to look at the intermolecular force that's observed between polar molecules. So when you have polar molecules, you have an end that's partially negative, that's where the more electronegative region would be, and a partially positive region, and that's where your less electronegative element would be. Because it's pulling less on the electrons, its electrons get pulled away, it becomes partially positive. So since these molecules don't exist in isolation, what we can say is that, well, if you have two polar molecules near each other, which you will in a solution, the positive end of one molecule is going to be attracted to the negative end of another. Now keep in mind, these are partial positives and negatives. This isn't as strong coulombically as an ionic bond where you have a complete positive and a complete negative. This is just a uneven distribution of charge, not like an ionic bond where you have a stealing. Okay, so two polar molecules will have an interaction between their positive and negative regions. And it's essentially, when they form a fluid solution, they're going to align themselves to continually have a strong amount of interaction between the positive and negative ends and try to minimize the repulsion between like charges. So you end up with a stacking that ends up looking something like that. Now we're going to look at a video where we show a solution of polar molecules. You can see that they're fluid, they're moving around, but as they get partially positive ends come near partially negative ends, they're going to form an interaction. That interaction is a dipole-dipole intermolecular force. One thing to keep in mind when you're comparing these to the London dispersion forces we're going to learn about in a few minutes is that this separation of charge, where you have the partially positive region and partially negative region, is permanent. It is a permanent dipole. It is much stronger than something that's temporary, okay? Because this is there all the time, as opposed to the London dispersion forces, which is only going to be happening some of the time. So keep that in mind as we learn about those. Now, sometimes with polar molecules, you have super-duper dipole-dipole interactions, and we call those hydrogen bonding. Now, hydrogen bonding only exists when you have a hydrogen bonded directly to and nitrogen, oxygen, or fluorine. Those are all highly electronegative elements that withdraw electrons very strongly from the hydrogen, leaving it very partially positive, and it leaving the nitrogen, oxygen, or fluorine very partially negative. Now, this can't happen if you have, say you had a hydrogen next to a carbon that was also bonded to a fluorine. It needs to be a direct attachment. So that's when you would observe hydrogen bonding. Now, hydrogen bonding is about 1/10 as strong as an intramolecular force known as a covalent bond. So they have large impacts on how matter arranges itself. Right? So these are just a step up from dipole-dipole interactions. Another interaction that you can have with polar molecules is between that and ions in a solution. We all know that water dissolves salt, right? You have oceans. And the reason that can happen is the result of the ion-dipole interaction. So when you have an ion dissolved in solution, or an ionic compound like salt, you have a positive sodium ion and a negative chloride ion. We know that in the water molecule, the oxygen end of the water is partially negative, and the hydrogen end is partially positive. And granted, this is only 2 dimensions, so 3-dimensionally picture there would be even more water molecules arranging themselves around the ions, but the negative end, the partially negative end of water is going to interact with the positive ion, so you have all the oxygens aligning themselves towards the positive ion, or cation, and then you have the partially positive hydrogen atoms aligning themselves with the negative ion, or the anion. So that is what an ion-dipole interaction is. Just the interaction between a dipole, or polar molecule, and ions that are present in a solution. In this part, we're going to talk about London dispersion forces. Now, London dispersion forces are the weakest of the intermolecular forces, and they exist between nonpolar molecules, and even polar molecules have them. But what essentially happens is you end up with a temporary shift of electrons building up towards one end of the molecule. What's going to happen at that point is you're going to have a partial negative region and a partial positive region. And when that happens on one molecule, when it comes near another molecule, it's going to cause their electrons to migrate towards a partial positive center. So then you end up with a lopsidedness on the other molecule. So you end up with an induced dipole on these. Now, this is temporary and instantaneous and nowhere near as strong as a permanent polar dipole. However, that is how they form. And then it goes away. But if these keep happening, especially with 2 molecules that have a lot of surface area in contact, what you're going to end up with them is making a considerable difference in how much energy it takes to pull them apart. So while they're weak, collectively in larger molecules, they make a huge difference. And again, they result from a temporary lopsidedness of electrons within a molecule that would otherwise be nonpolar, where you have a buildup of electrons on the negative side, resulting in an electron deficient area, which then you would consider partially positive, and then coming near another neutral atom that will draw, or molecule, it will draw the electrons toward that positive center, leaving the other area electron devoid, and then partially positive. So that is how London dispersion forces work, and that's what an induced dipole is.